Hello again and welcome back to SNC1W. We are on Unit 2, Lesson 5. As a quick review, in Lessons 1 to 4 we discussed the state's classification and properties of matter, the history and structure of the atom, isotopes and radioisotopes, and calculating average atomic mass. We then dipped our feet into a discussion on the periodic table and then dove headfirst to review trends in the periodic table. Today we will be talking about the Bohr-Rutherford's model of the atom. The learning goal for this lesson includes explaining the relationship between the position of an element in the periodic table and the structure of its atom. Success criteria, or knowing that you have absorbed all of this lesson's knowledge, can be determined by whether you can complete the following tasks. Ask yourself, are you able to draw a Bohr-Rutherford diagram of different elements, calculate the number of electrons by using an atomic number from the periodic table, and determine valence electrons? The specific expectations targeted within this lesson include C2.3 and C2.4. Niels Bohr was a Danish physicist who made significant contributions to the understanding of the atomic structure. In 1913, he conducted a series of experiments where he studied the light produced when atoms were excited by heat or electricity. This led to the development of his atomic model, which proposed that electrons exist in discrete energy levels around the nucleus. This model was a major breakthrough in our understanding of the atom and helped to explain many of the properties and behaviors of elements. Bohr's work laid the foundation for further research in the field of quantum mechanics and has had a lasting impact on the field of physics. In a previous lesson, we discussed Ernest Rutherford's gold foil experiment, which found that the vast majority of the alpha particles pass straight through gold foil, indicating that atoms are mostly empty space. However, with a small fraction of the alpha particles deflecting at various angles, he learned that they had interacted with a positively charged nucleus at the center of the atom. This led to the discovery that atoms consist of a small, dense, positively charged nucleus which is surrounded by negatively charged electrons orbiting at a distance. Unfortunately, Rutherford's model of the atom failed to explain why atoms of different elements produced unique colors. This led to the development of Bohr's model, which proposed that electrons moved in specific orbits around the nucleus and could jump to higher orbits when excited. When these excited electrons fell back to their original orbit, they released energy in the form of light. This explanation helped to clarify why different elements produce distinct spectral lines and revolutionized our understanding of the atomic structure. According to Bohr's model of the atom, electrons move around the nucleus of an atom in specific orbits, much like how planets orbit around the sun. Each of these orbits, or energy levels, can hold a specific maximum number of electrons. The closest orbit to the nucleus has the lowest energy and can hold a maximum of 2 electrons, while the outermost orbit has the highest energy and can hold up to 8 electrons. This model was the first to explain the spectral lines of hydrogen and laid the foundation for further development in quantum mechanics. A Bohr-Rutherford diagram is a way of representing the arrangement of electrons in an atom. The diagram shows the nucleus of the atom, which contains protons and neutrons, as well as the electrons arranged in different energy levels or shells around the nucleus. Each shell can hold a certain number of electrons. As discussed, the first shell can hold up to 2, with the biggest shell ability to hold up to 8. The diagram helps to illustrate the electronic configuration of an atom. It is a useful tool for understanding the properties and behavior of different elements. In summary, the Bohr-Rutherford diagram is a simple model used to visualize the atomic structure of an element. So to create one, we start by locating your element on the periodic table and determining its atomic number. In our example, the element chosen is carbon, and the atomic number is 6. The number of electrons in an atom is also equal to its atomic number. Therefore, with carbon, the atomic number is 6, so that means the number of electrons is also 6. Once you have determined the number of electrons, you can draw them around the nucleus of the atom. Remember, the first shell can hold up to 2 electrons, while the second shell can hold up to 8. If there are more than 10 electrons, you would need to add additional energy levels. In our example, our first shell would have 2 electrons, while our second shell would have 4, equaling a total of 6. Of note, the electrons should be drawn in pairs with opposite spins. This diagram is a useful tool in understanding the basic structure of an atom and can be used to predict chemical properties and reactivity. Okay, so we learned that the Bohr-Rutherford model is a simplified model of the atom that helps us understand the arrangements of electrons in an atom. To use this model, you first need to identify which period or row your element is in on the periodic table. This will tell you how many energy levels the element has. Elements in the first period only have 1 energy level, while elements in the second period have 2 energy levels, and so on. The number of energy levels an element has corresponds to its position on the periodic table. By understanding the number of energy levels an element has, we can start to understand how its electrons are arranged and how it interacts with other elements. Let's go through an example together. To draw the Bohr-Rutherford diagram for fluorine, you would first need to determine its atomic structure. On the slide, we can see that for the element, fluorine, shown on the periodic table as the symbol F, our atomic number is 9. You can find this number in the upper right corner of the purple box over the fluorine F symbol. As mentioned, this means that fluorine has 9 electrons, as the number of electrons is always the same as the atomic number. Fluorine has 9 electrons, meaning it has 9 protons in its nucleus. To determine the number of neutrons, simply subtract the atomic mass found under the element letter by the atomic number. In our example, that would mean 19 minus 9, which equals 10. Within the nucleus, we would write the number of protons. In this example, we have 9, and the number of neutrons. In this example, we have 10. Great, so now we have our nucleus. Before moving on, can you remember how many electrons can fit in the first orbit? The answer is 2. Okay, so now we have a nucleus showing that our element has 9 protons and 10 neutrons. We then draw our first orbit, or energy circle, around our nucleus. As we have learned, the first energy level can hold a maximum of 2 electrons, so please draw those. Now determine how many electrons are left. To do this, we would simply subtract our total number of electrons from the 2 drawn in the first orbit. So in our example, 9 minus 2 equals 7. Now we know that we need to draw 7 more electrons. But our first energy level is full at 2, so we draw a second energy level. We previously learned that the second energy level can hold up to 8 electrons. Therefore, 2 electrons would be placed in the first energy level, and the remaining 7 electrons would be placed in the second energy level. Here is a visual example of our diagram, again showing the nucleus in the center, 2 electrons in the innermost energy level, and 5 electrons in the outer energy level. For the next few slides, I would like you to create Bohr-Rutherford diagrams. As a reminder, to draw the Bohr-Rutherford diagram, you would typically first need to determine its atomic structure. Remember that the number of protons and electrons is the same as the atomic number. To determine the number of neutrons, you would simply subtract the atomic mass by the atomic number. Within the nucleus, we would then write the number of protons and the number of neutrons. In the examples on these slides, the nucleus has been created for you. Next, you would simply draw your first energy level and add up to 2 electrons. In our example for hydrogen, we see that there is only 1 proton, meaning there is only 1 electron needed. So we would only need to draw 1 electron on our first energy level. I would like you to complete the reviewed steps to draw a Bohr-Rutherford diagram for boron, and then identify whether the diagram on this slide is correct or not. If it is not correct, how would we fix it? The Bohr-Rutherford diagram for boron shows a nucleus with 5 protons and either 5 or 6 neutrons, depending on the isotope. In our example, we use 6 neutrons. Please pause this slide while you draw your Bohr-Rutherford diagram. If you guessed the first diagram was incorrect, due to too many electrons in the second orbit, you would be correct. Let's go through the correct example together. The Bohr-Rutherford diagram for boron shows a nucleus with 5 protons and either 5 or 6 neutrons, depending on the isotope. In our example, we use 6 neutrons. With this, we know that we need 5 electrons, as this is the same number of protons. There are 2 electrons in the first energy level and 3 in the second, totaling 5 electrons altogether. This model is correct. I would like you to complete the same steps for magnesium and then identify whether the diagram on this slide is correct or not. If it is not correct, how would we fix it? Please pause this slide while you draw your own diagram. If you said the above diagram was correct, you would also be correct. The Bohr-Rutherford diagram for magnesium shows a nucleus with 12 protons and 12 neutrons. With this, we know that we need 12 electrons, as this is the same number as the protons. We place our maximum of 2 electrons in the first energy level and our maximum of 8 in the second energy level. Within this example, we need to draw a third energy level in order to add the remaining 2 electrons, totaling 12 altogether. Just as a reminder, valence electrons are the electrons located in the outermost shell of an atom. These electrons are involved in chemical reactions and are responsible for the chemical properties of an element. The number of valence electrons in an element determines its reactivity and bonding behavior. For example, elements with a full valence shell, such as noble gases, are generally unreactive, while elements with one or a few valence electrons tend to be highly reactive and readily form bonds with other atoms. Understanding valence electrons is important in predicting a chemical reaction and understanding the behavior of elements in the periodic table. That brings us to the end of Unit 2, Lesson 5. I hope that by the end of this lesson, you are more confident drawing Bohr-Rutherford diagrams of different elements. Next lesson will be our final lesson within Unit 2. And with that, we will say bye for now.